So this problem is described as in this polynomial ring Rx. Again, the R stands for what the coefficients are from. They are real numbers. The X being in square brackets emphasizes the elements of this ultimately are polynomials. Let A be all the polynomials in here with a constant term equal to 0, no constant term. What we want to prove is that A is the same as the principal ideal generated by X. Perhaps it's best to think in terms of set inclusions here, to do this in 2 steps. First, Y is a subset of the principal ideal generated by X. What would we have to prove? Give me an arbitrary polynomial with constant term 0. Why is it a multiple of X is the key. Give me an arbitrary polynomial. How could I write an arbitrary polynomial? Well, maybe like an x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2. I don't know what the degree is. Doing an arbitrary degree n here. Plus, etc. These a's are all real numbers. They're all real numbers. If it's an element of A, that means it's got a constant term 0. So the last few terms are a2x squared plus a1x plus, don't write a constant term. The constant term 0. I mean, I could write plus 0, but I don't need to. What do I want to show? I want to show this is a polynomial multiple of X, because that's what this principal ideal generated by X is. All polynomial multiples of X. In other words, I got to write this as something times X. Factor out the X. These continue to be real numbers. I can factor out the X. This is X times an x to the n minus 1 plus an minus 1 x to the n minus 2 plus an minus 2 x to the n minus 3, etc. through a2x plus a1. I've written it as a polynomial multiple of X. I wrote the X on the left. I could have written it on the right. This is a commutative ring. By definition, this is an element of the principal ideal generated by X, because it's a polynomial multiple of X. That's enough to verify A is a subset of the principal ideal generated by X. What about the other inclusion? That the principal ideal generated by X is a subset of A. In other words, every polynomial multiple of X has a constant term of 0. Well, in essence, it's the reverse calculation. Although maybe you'd use slightly different notation. Maybe you say, okay, I've got an arbitrary polynomial of degree n, and I'm multiplying it by X. This arbitrary polynomial of degree n possibly does have a non-zero constant term. There is an arbitrary polynomial. To be an arbitrary element of the principal ideal generated by X, I got to multiply that by X. That is an arbitrary element of the principal ideal generated by X. Is it in A? Does it have a constant term of 0? Multiply it out. You'll get a constant term of 0. So it's a slightly different notation, you might say, because I'm thinking about it differently. But it's really, in essence, the same idea. Just reverse the calculation. Different notation in red and green, slightly different, but basically the same idea. You've got both inclusions being true, therefore the equality is true. I'm imagining maybe you didn't think to write this kind of thing down, but I hope you were at least able to maybe think about it. Maybe write some words down. But this would be how you'd show it symbolically. And since that by definition is the principal ideal generated by A, and since we proved such things are ideals, that means A is an ideal as well. You could use the ideal test here too. Think about it with me here. There's first of all, A is certainly non-empty. There are polynomials with constant term 0, infinitely many such. Certainly it's closed under subtraction. Give me two polynomials with 0 constant term. When you subtract them, there's still going to be a 0 constant term. And it's super closed. When you multiply it by an arbitrary polynomial, it'll still have a 0 constant term.